Very good morning and thank you very much. It's obvious that we have a very lively group of directors here and also that you're all very familiar with each other. My name is Serina Hijjas and I'm just your host today from Theseira from Climate Governance Malaysia. Welcome to the second series of the Masterclass from Climate Governance 2024. We have a series of about 6 talks and this is the second one. And we have Dr. Theseira today, who will be giving his talk and will make his introduction much later. The Director's Masterclass is to elevate your proficiency in all areas of climate change with the latest insights and shifts in the market pertaining to sustainability. This Director's Masterclass is a collaboration with FIDE Forum and jointly hosted by ASEAN School of Banking, Bursa Malaysia, Securities Commission, and in collaboration also with ICDM, who is publicizing this event. This masterclass will be recorded and uploaded to the CGM YouTube channel, but we won't be showing any faces of those who are doing the questions. We're just recording for record, so just to be careful of the privacy. For those who've not been to the Masterclass 1, you can catch Masterclass 1, which is very, very interesting on the YouTube, and we play that back. The notes and slides will be made available to you after this talk today. A bit of housekeeping. Maintain phones on silent and please put it in your bag. On the table means there's too much temptation to check. So it's not only the millennials that are sort of checking, but it's you know, let me update it. 1.5 hours is all the time we need, so I think, you know, nothing's going to crash. Please do ask appropriate questions. We treat this as a sort of fire chat masterclass. And Gary, no matter how difficult it's going to be, will be able to answer it for you. Let us start with the introduction and welcome speech from Tai Kai Lun. He is the Chief Executive Officer of FIDE Forum. He's the reason why we are here. He spearheads the implementation of strategic initiatives steering FIDE Forum towards his vision of becoming the foremost advocate for corporate governance excellence within the boards of financial institutions licensed in Malaysia. For you who may not know, he is also a prolific author. He's written 3 sustainable books, and he has many other accolades, of which you can look up later and you will see. And he's as a very much sought after speaker at international conferences. So without further ado, let me introduce Luan.
I've always been known to have a very loud voice, so effectively I don't really need a mic, but nonetheless. Good morning everyone, friends, members, colleagues, old friends, new friends, whatever. Welcome to FIDE Forum series on climate. I just want to say a couple of things before I hand over the mic to Gary. I would like to say that many climate observers would tend to agree that it would be absolutely an uphill task for the global community, which involves every one of us, to achieve the targeted 2% or 1.5% increase in global temperature by 2050. I think that's a fact that some of us are still in absolute denial. So we might as well be ready to adapt to the worst case of 3% increase by 2050, if at all we are still alive by then. At the current rate of global warming, some people call it global boiling now, scientists are already predicting that global temperature will hit 3 degrees anyway by the end of this century. That I'm absolutely sure none of us will still be around. Okay? Or even earlier. A new study that I discovered last month, published by the Direct Science, they predicted that between 2020 and 2100, the Indian Ocean, which is a very large space that they occupy, could warm at the rate of up to 3.8 degrees Celsius per. and therefore the unfolding of what you already have seen or read on climate onslaught of excessive heat, floods and droughts have already exceeded climate experts' prediction. It's a very daunting task right ahead of all policymakers and governments. Welcome to today's session on climate science, a topic that we thought would be relevant, and it is to be presented by Dr. Gary Theseira. He's been around for some time now. No other experts we could invite to give this talk as part of our intent to share as much as we can with the policy movers and shakers within the financial industry. Many thanks also to the Climate Governance Malaysia, CGM, for this collaboration. So Gary will not talk about solar panel. He will also not talk about EV cars. But his focus very much will be on forces behind the global phenomenon of global warming. And as a footnote, I thought just want to share with you. Reason why I know a little bit more is because I need to read in order to write. Is that global warming was first discovered as a greenhouse effect. In fact, greenhouse effect, a terminology that we are first known as, way back in 1824. That was a long time ago. I think that was during the time of Industrial Revolution. But a breakthrough paper only 70 years later pinpointed that human activities had to do with the burning fossil fuel that causes this global warming. Then it wasn't until the mid-20th century, that was after the World War, that the CO2 became clear and future danger. The rest of it is history. I think the next 50 years will be a challenging one for every one of us. We thought that this session will shed some lights onto the forces behind the climate science. Most of us would have gone through classes on data science. I think this is an interesting topic, at least as an opener. And I hope that you will appreciate as much as I would do in listening to Dr. Gary for his presentation. Over to you, Gary.
Thank you. Can I call you Kailun? I'm not sure.
Yes, Luan.
Luan.
Yes.
What's that? All right. So let me introduce Dr. Gary. He's a technical expert trainee at Malaysian Green Technology and Climate Change Corporation, MGTC. He has more than a decade of experience in climate change and sustainability policy development and negotiations at the international national levels, and a very skilled communicator, which you will hear later on climate science. So session 2, what directors must know about latest developments in climate science, is in today's business realm, what members must grapple with the urgent imperative of addressing climate change. A lot of the annual reports are coming out now from the big corporations like IGN, etc., which basically outline their environmental strategies. So we'll be seeing more and more of that as we move on. Mastery of climate science is no longer optional. It's essential for understanding the environmental risks and opportunities and building resilience for your business. With this knowledge, boards can navigate challenges, size sustainable opportunities, and foster trust with stakeholders. So, Dr. Gary.
A very good morning, everyone, and let me join the others in welcoming you to this session of the series that we have for Masterclass for directors. For those of you who have heard me speak before, thank you for coming back. I really do appreciate seeing the familiar faces. It's always humbling to know that whatever I say, hopefully will find a home somewhere. Let me reiterate what Serina said earlier. Do feel free to stop me at any point in time. I didn't choose this title, Climate Science. It was chosen by Datin Sri Sunita, Chair of the Directors of Climate Governance Malaysia. And it was a bit of a curveball for me, because those of you who have heard me speak know that I tend not to focus on the science for a couple of reasons. The first reason is I'm not a climate scientist. I'm not a climatologist. Right? So if you ask questions that go really deep into climatology, I won't be able to handle them. The second reason is that actually when the climate science is more frequently misunderstood than it is understood. Because to answer a question, you need to have so many qualifiers, like any good scientist will have, right, that it becomes, too much of a mess, right? So I find that the climate science actually, what it has done is it has actually confused people more than anything else. And what I hope to accomplish today is to give you a sense of how the science works, why it's a process of making mistakes, recognizing the mistakes, understanding why the mistakes have been made, and then making the corrections. And you're doing this not in a vacuum, but you're doing this in an ecosystem that involves the environment, the social, the geopolitical, and all of these things. So as directors, I think being at this 40,000 feet level, I hope that what I'm going to talk about today will actually make a bit of sense. All right. The reason why I have that as the title slide is that icing is a problem for aircraft. You may not think that's associated with climate change or anything else, but it is something that's deeply linked to one of the biggest controversial discussions in climate today, and that's the impact of supercooled liquid clouds. We'll get to that at the end. But in actually, where we're going to start with is actually this concept of the carbon budgets. Exactly how much do we have? Why do people say we have this much left? Why do some people say we have this much and then change and say we have even more or even less? Why do the dates keep shifting? We have to hit zero by 2045, hit zero by 2040, by 2035. What do all these numbers mean? And why do they keep changing? Then, where are we now? Big news, 2023, warmest year ever. What does that mean? Last 12 months, even warmer. What does that mean? We've crossed 1.5. Okay, now is this crossing 1.5 once or crossing 1.5 for always, or are we somewhere in between? How do we understand this shifting goalpost thing, right? As directors, we are faced with these questions. When somebody poses this kind of question, right, I really feel compelled to say, okay, wait a minute, let's back up a little bit and let me explain why these things are happening. What made 2023 and the January of 2024, why this tipped the scales in the way it did. And then we'll talk about some big systems and why what happens in the big systems is very, very important. Pacific is a huge system, and I'll talk about two phenomena in the Pacific. We'll work on that. And then the other one that is hot on, or rather it's sort of the next target, is the Arctic, right? The Antarctic is too big of a target. There's no shipping that goes to there. It's a big landmass anyway. Countries have decided to share it, et cetera, et cetera. Those of you who have been on these Antarctic tours appreciate that. But the Arctic is much, much, much more accessible, and it's much more tempting, given the fact that if we don't have sea ice there, it's a shortcut. All right, so what are some of the risks, what are the threats coming out of the Arctic? It's not all sea ice, there's Greenland, which we need to think about. Then we'll talk about these supercooled water clouds, and then the latest thing that climate scientists are arguing and fighting, and coming to blows about, which is this concept of climate sensitivity. Which parts are sensitive? And you can look at it that way too. Climate scientists do get sensitive about what they're researching, all right? So when I talk about climate sensitivity, I'm not talking about the climate scientists being sensitive. We're actually talking about the big picture, how climate is sensitive and why we should appreciate that. We'll talk about some good luck. Half the time, we're survivors on this planet because of dumb luck. We didn't do anything to earn it, nothing. It's just serendipitous. Okay, our lives have been saved. So how do you deal with those kinds of things? And then some concluding thoughts. All right, so in 2010, we were coming out of the Copenhagen debacle, all right? Everything blew up in Copenhagen, multilateral process blew up. People were really in very low spirits, low point in time. The next COP was in Cancun. In Cancun, they said, let's look at this 2 degrees. Let's adopt this 2 degrees as something solid, something permanent that we can work on. And we said, okay, if we choose 2 degrees, then how much do we have left? Okay, and when should we finish using it? So if you look at this slide, what it boils down to is that to stay below this 2 degrees, which we agreed in Cancun, we can only afford to release 485 gigatons. Okay, here you will see it's picograms, but it's the same thing, just more grams and fewer tons, right? And we have to hit that 0 mark by 2045, all right? Now, when the small island developing states looked at this, they said, no, 2 degrees is too much. So that brought up the big discussion for the scientists to discover what the difference between 1.5 and 2 degrees actually was. Right? Were the concerns of the small island developing states, places like Palau, Kiribati, right, who are already wading in ankle-deep water? Okay, what's the truth there? All right? So this is it. This difference between 1.5 and 2 degrees, what we see twice the rate of plant loss species. For insects who do all the pollinating around, 3 times worse, a half a degree. Coral reefs, about a third worse. Right? Extreme heat, 2.5 times worse. Right? And then sea ice in the Arctic loss, 10 times worse. Right? So when you look at this, then you have to ask, okay, so is it worth it to try to go to 1.5, given the difference between 1.5 and 2 degrees? So what does half a degree, what difference does half a degree make? All right? So it turns out that globally, we still have a bit of a conscience, and we said, okay, during the Paris Agreement negotiations, we'll put up there 2 degrees because it's already been adopted, but we'll add and 1.5 degrees if at all possible. All right? So that's what then brings us to this 2 degrees versus 1.5 degree debate. So pretty much everyone says yes, 1.5 would be much better than 2 degrees, but haven't we already passed that? Well, yes and no, it depends. All right? That's kind of the next thing that we'll talk about. But before we leave this, we need to see, okay, if it's not 2 degrees, if it is 1.5 degrees, then instead of that 400 and some odd gigatons that we had, what we actually have is something more like if we, and it's tied to percentages, by the way, it's tied to probabilities, right? So if you're comfortable with this probability being bigger, then you can do all kinds of rubbish stuff out here, all you want, right? But if you want to really nail this and say, okay, I want it to be close to 75%, 80% probability to hit it, then I have to pull back on this scale a lot, all right? That's why there are 2 ways to get to this 2040 date. You can do it this way in the dark blue and put fewer greenhouse gases in the atmosphere, or you could do it with a straight line, 400 gigatons, and put a bit more greenhouse gases in the atmosphere. So there are many ways to draw this line from this point to that point, all right? But it makes a difference. What you put in the atmosphere makes a difference. That's going to either accelerate or decelerate the changes that we see in climate, all right? So when you hear numbers, 340 gigatons, well, what's your qualifier? You know, is it by 2040? Is it by 2045? Is it by 2035? All right? So these are the questions that should pop up in your mind when you understand. And don't panic. See, so you should feel comfortable now in asking for that backup information. Right? There's nothing to say, oh, I don't know what this person is talking about. He's talking about this date. I never heard this date. I thought I read a different date earlier. You know, it's not like that. It is a discourse. Feel free. No, I read that we need to stop this by 2040. Oh, that's because you're talking about 67% chance. I'm only talking about 30% chance. If I'm only talking about 30% chance, then I can be way out here. I don't care. All right? So once again, it really is wide open in terms of all these numbers. It's a combination of all these things that work out to give the numbers that are quoted out there. Please.
Sorry, Dr. Gary.
Yeah.
So how are we measuring that globally, and how accurate is that number?
Okay. So how are we measuring that globally? We are measuring that globally using a series. So question. Huh? How are we measuring that globally, and how accurate? Huh?
Yeah, how accurate
Okay.
is that? I mean,
Yeah.
depending
Yeah.
on the country giving
Yes.
that information.
Yeah. Actually, we measure it from 2 directions, top down and bottom up. And what you're asking is from the bottom up. How do we actually... now, most countries have actually come to grips with the fact that they actually do have to make factual reports. At the national communications, the biennial update reports are all reviewed by experts. And so they know really if a country is but even before they get there, there's a lot of ways that countries can cheat. For example, if emissions are classified for some reason, US military, 0, right? No emission sources from US military. Why? Because it's classified. Right? So there are enough loopholes, places where you can hide your emissions if you're one of the world superpowers, right? That you don't have to worry about this. But the rest of it, the consumption emissions, are things that we actually can work on, right? Working from the top down, we have a series of sensors in the middle of the Pacific, pinned in Hawaii and then moving north and south. And we actually do measure total atmospheric CO2 concentrations. So we are tracking that very closely. And the reason why we choose the middle of the Pacific is because it's very pristine in terms of air quality. You're not going to have outliers because of false information. All right? So once again, it seems like you've got moving targets, but actually all you have is combinations of numbers that you should begin to feel comfortable about using as the global budget. By 2040, we need to not bust this budget of 340 or 400 gigatons. Right? You want to move this number higher? Sorry, you want to move this, where is it? You want to move this number higher, then this curve has to move back. You're comfortable with this number, you are comfortable with this number being fairly low, then you can move it out. All right? Okay, so that's the budget. So we use the budget to plan. But the fact of the matter is the budget's already broken. Because all the countries know how much they're emitting every year, and they know that if they only plan to hit net zero by 2050, then what are you talking about 2044? Right? Some of the EU states, Finland, etc., 2035, net zero, serious, very serious about it. Okay, on track. All right, most of their mobility is already electrified. Okay, they're off coal already. They've got some gas running it, but so some countries take it very, very seriously. But as far as the big, Canada, US, etc., difficult to see how they'll actually be able to fulfill that. Right? The EU, once again, very serious about this. They collect good data. They analyze it well, and they actually make a very good job of presenting it in a way that's understandable. In particular, this Copernicus project, all right? And based on this, we already know that 1.1 is already there. I mean, it's square bang in the middle of the range. All right? We have warmed 1.1 degrees. What we've also found out is that if you look from January to December of 2023, yes, historically the warmest year on record ever. All right? So the global increase there is 1.48 degrees. Okay, so we're getting dangerously close to the 1.5 degrees. Not there yet if you look at this calendar year. Right? But if you add the very next month, January 2024, guess what happens? Go from February to February of 2023 to January of 2024, and you break the 1.5. It's now 1.52. All right? So should we all just give up and go home and climb into bed and whatever it is where we feel safest, so curl up into a cocoon and say, no. But so you've got calendar years, you've got 12-month spans. So all of these things are out. So, and these things hit the headlines in many different ways. Hottest year ever, and hottest 12-month period ever. So understanding how to read these things is really half the battle. And when you do understand how to read it, then you begin to see, okay, now I'm going to show you something else about this that's going to help you understand even further about how this should be understood. This actually is this actually is a live animated web page that you can find up there. It's copernicus.eu. Okay, it's got a slider at the bottom. You just place your mouse on the slider and you slide it from 2000 all the way up. Okay, and what it does is it gives you the slope of this curve based on a 30-year interval. So you move the slider, you move the 30-year interval, it picks up different data, and it changes the slope of the curve, which then tells you when you expect to hit 1.5 degrees. It's very nice, very interactive. You can see all kinds of things when you look at this. To begin with, when you look at a graph like this, you see that this is smack bang in the middle of the high confidence range. All right? So IPCC has got a range. They believe that this is the highest probability, and you are smack bang in the middle of it, which puts you in fairly good stead. You're fairly confident at that point. All right? Now, as we move the slider along, oh wait, sorry, I need to point out that date. May 2045. That's when we're supposed to hit 1.5 degrees had we placed the slider at the year 2000. We moved the slider to 2015. Why? That's a good year, Paris Agreement year. Yeah, COP, that agreed to Paris Agreement. But now, what happens is we're using a different interval, and we're at March 2045. We've moved it quite a bit. I moved the slider to 2019. So we're talking about 89 to 2019. It's now 2036. Okay? And then I move it to 2023, rather, yeah, 2023. All right? And this is July 2023. It's now at February 2035. And if I add the most recent, look, this is, you see these data points up here? Yeah. I move it to March 2024, which includes January 2024. All right? We're now at July 2033. All right? So when you hear all these different dates about when are we supposed to hit 1.5 degrees? Right? And so now we went from being in the middle of this range to being very, very close to the top of this range now. We're moving to the edge. We're going to become that. And in fact, if you look at this highest point here, it's actually way above 1.5 degrees. In fact, it's out of the range already. So it started getting out of the range here, but here it's completely out. Okay? Right. So now, what are the chances of staying there? Probably not so much. We look at behavior in the past. It's gone up, it's come back down. It's gone up, comes back down. That's what this range is for, right? But when you hear, when you hear the alarmist calls, we're out of our expectations. Does it mean that all the models are wrong? Does it mean that the confidence interval is wrong? Okay, so these are the kinds of science questions. Hopefully that science will continue to communicate using these kinds of things. But it just helps you understand. Just because it's up here now doesn't mean it's going to stay up there, right? But we need to understand why it's there, all right? And that's the next thing that we're going to look at in a little bit. So some important things here. This date has shifted from there all the way back to here, and chances are, if the temperatures continue to be high, they will continue to remain there. But once again, if they drop, then we'll tend to move that line back out again. And you can see the 30-year interval, is a fairly reasonable interval to use. It's a long time. It's enough time to raise a child into an adult. Okay, one generation per se. Okay, any questions on this? It's nice. Find this web page and play with the slider. Okay, so these things make communicating the science a little bit easier. Yes, please, sir. Yeah.
Just check with you. Mm-hmm. The graph there is quite concerning. How do we take into account all the efforts that have been taken to counter the issue about degreening? Basically, the issue about carbon.
Decarbonizing.
Decarbonizing.
Okay. This actually, by the way, it's always tempting to try to correlate what we see with what we're doing. And that's actually one of the big difficulties in the science itself. The science hasn't adequately communicated the fact that what we do today will only impact climate 10 years, 20 years from now. What we are seeing now is actually the impacts of our actions 10 years, 20 years in the past, but coupled with what's happening right now. Okay, and we'll see that when we get to the sensitivity part. Thank you for that question, but there is a decoupling of that. So you really have to think very broadly in terms of how do we change this part of the curve, 2050. You see, because what we're doing now is to make changes out in 2050, 2060. All right, maybe some of us might not be around, but that's the objective. There's quite clear agreement that nothing that happens tomorrow or next year or even 5 years from now is due to what we as a civilization do today. Yes, sir? Sorry.
No, just a question. During the pandemic, where the carbon was probably at the lowest, transportation, et cetera, the needle on the tonnage did not go down in Hawaii measured.
Mm-hmm.
It actually was still ascending.
Yeah, ascending. Yeah.
And the idea behind that is that we're actually suffering from industrialization of 10, 15 years ago, and it's still catching up.
Mm-hmm. Yeah. So the issue is that we have got sinks that are saturated. Okay, the reason why the developed world got a free ticket was when they began industrializing and using coal in a huge way. The sinks were empty, and so everything they put in the atmosphere, sea absorbed it, forests absorbed it, ecosystems absorbed it. So it never reflected as a change in the atmospheric concentration. Right? Now that the sinks are almost saturated, in fact, the sinks are giving back now. They're re-emitting. You give it to the sink absorbs, gives it back. Give it to the ocean gives it back. You give methane to water behind the dam. The moment it hits the spillway, it vaporizes, the methane flashes out again. So it's some of these systems are actually giving back. All right? But thanks for the question. The idea really is that it's not reflected in the atmospheric CO2 concentration. It's reflected in the numbers that we ourselves generate, the emissions reductions during the pandemic. Yes, sir?
There's also such a thing as positive feedback loops, right?
Oh, yeah, absolutely. Yeah.
So, I guess...
I'll get to feedback later on, yeah. But you're absolutely right, positive feedback loops as well. Things associated with the melting of the tundra, etc. Yeah, and methane clathrates in oceans and things like that. Okay, so if we weren't responsible for 2023 through the emissions of the last 5 years, 10 years, what was? Okay, so let's take a look. Extraordinary year, drought, rainfall, heat waves, particularly in the southern hemisphere, even though most of the emissions are in the northern hemisphere, right? The impacts went all the way down to Antarctica. One of the biggest reasons for that actually was the fact that we had, after 3 years of La Nina, a year of El Nino, right? How should we understand this? I said earlier, the Pacific is a huge system, okay? And this is not how you might conventionally think of a graphic. This is basically the Western Pacific and the Eastern Pacific. Okay, so this is like the coast of Chile or Peru, Ecuador, and this would be of. Oh, I'm sorry. So the left side of this picture is the Western Pacific, our side of the Pacific, and this is the South American side of the Pacific. And this vertical axis is actually time. Okay, so we start at June 2023 at the very top, and then we come down September 2023, November 2023, and then all the way to April and May of 2024. So it's very current. We know these numbers for sure, right? And what we see is at or about July of 2023, we get the classic El Nino. Warm water amassed on the eastern Pacific off the coast of Peru, Bolivia, etc., all right? And cold water here on our side of the Pacific. Now, if you remember anything about El Nino and La Nina, of course La Nina is the opposite, right? And you can actually see the La Nina beginning to form here, all right? But the idea really is that if you look at the duration of these phenomena, first of all, they're natural. Okay, that's the first thing to know. They're natural. They happen. Indian Ocean dipole, you know, all these things are natural. Circumpolar currents, jet streams, all natural, right? And they are cyclic. Right? El Nino, which brings us dry weather, all right? Thankfully, the duration tends to be over the scale of months, between 4 months to 9 months in length. La Nina, 1 to 3 years. Okay? Good for us. Why? Because we can handle droughts over short periods. We don't want 3 years of drought. We don't want La Nina with you know, dry for 3 years and then, you know, forest fires, so we can't grow crops. So we can handle the rain, extra moisture for 3 years. We can't handle drought for, you know, more than a year. So it's good that for us, once again, did we do anything to earn this? No. Serendipitous. Right? We could have been on the other side of it and have the opposite situation. Right? So we see that classic El Nino, warm water there, cold water there, and then as the year ends, the warmth tends to move over to this side, and then by April, we begin once again to see the cold water upwelling on the Peruvian coast, bringing up the nutrients, you know, which is once again going back to the longer La Nina cycle, right? So the wind normally blows this way, east to west on the Pacific, because the world is turning west to east, right? So the wind counteracts that, and this is the way it is most of the time, and then occasionally we'll pop back into El Nino and come back. But El Nino was very severe this year. Okay, it was not long. The duration wasn't long, but it was fairly intense. Okay, look at the color intensity there, as much as 4 degrees higher SSTs. Okay, it's not sales and service tax, by the way. You see SST up there as sea surface temperature. Okay, sea surface temperature. So you know, you blow across surface of the water, it moves. So prevailing winds blowing from east to west bring the warm water to the Western Pacific, and that's the classic, you know, sort of as a default setting. So the El Nino is kind of when it gets flipped. All right. If you look at if I pull out then and get rid of that time element, you can look at the whole world. October 2022, we see cold water still up there off the coast of South America. Then in May 2023, El Nino developing and then spreading westward and then finally dissipating, and once again the cold water beginning to well up again on the coast of Peru. So, you know, do we know how intense, how long these things are going to happen? Do you know if they're going to shift? They're going to change behavior? Because if they ever do, we're in big trouble. If La Nina ever goes to months and El Nino goes to years, we are in trouble. Okay? But at least we know what happens when we have an El Nino, because El Ninos are sort of the intense part, and they do tend to disrupt how we would normally live our lives. Okay? So all the agriculture in the world, all the transportation in the world, all kind of is built on the consistency of La Nina situations or neutral conditions. And then they suffer when we have El Nino conditions. How do they suffer? Okay, if we look at temperature impacts, every time there's an El Nino, we are going to be warmer. The Indian subcontinent is going to be warmer. The entire South American continent is going to be warmer. The North American continent is going to have these dry spells, droughts in the northwest, really bad for the temperate rainforest up there. Fires, when they occur in the temperate rainforest, not good. All right. Northern Europe tends to be very cold. The Iberian Peninsula tends to suffer from heat stress. Your olive oil. Fires in 2022, 2023, I can't remember exactly when. The entire Mediterranean surrounded by fires. Okay, we lost thousands and thousands of hectares of olive oil. No mystery why olive oil prices are high. All right. If you rely on wheat imports, okay, from Australia, think about this as well. Now, this temperature map then also reflects in terms of the precipitation. Drier conditions, all of Southeast Asia and parts of Oceania. Okay, South Africa here, very, very bad. The Sahara in deep trouble. And once again, the Indian subcontinent. Difficult to handle when we have the high temperatures and we have low rainfall. All right. So once again, we are fortunate, serendipitous perhaps, we have this on the scale of months as opposed to years, and then we flip back over to La Nina. But it just so happens that 2023 was a bad El Nino year. Okay? But as you saw from the time, we've passed it now. The next question is, well, what's next year going to look like? Okay? All right. Besides that anomaly for 2023, we also had what I would say is the most underrated and underreported volcanic event ever. And part of the reason is it only killed, well, as far as we know, it only killed 5 people. Okay? But it was this Hanga Ha'apai volcano in the middle of the Pacific, where nobody is anyway, and people knew it erupted only when they heard the boom, basically. Okay, but a big boom it was. Now, excuse me while I grab this, because I need to place the cursor there and that. Okay, so to give you a sense of scale, that's the Tongan Islands on the lower right, where the volcano is, and Fiji is 804 kilometers away. Okay, so the size of that is extremely substantial. If this explosion had occurred anywhere else, North American continent, here in Southeast Asia, in Sumatra, very, very bad news. Like, why didn't we hear about this? I mean, people actually heard it, but after we heard it, we never heard about it anymore. But it's huge, okay? And if you continue, see, what's cool is the shadow, right? The sun is shining, and you see the stark shadow, and the sun is setting in the west. And as you continue watching it, okay, I'm geeking out a little bit, okay? but you kind of get, where is my cursor? Why can't I see the cursor? I had it earlier because of, there we go. The sun is setting, it becomes night, and the lightning and the glow from the arc is now starting to light that up. All right, and you see the shock wave. What's the... And this shock wave went around the Earth several times, okay, in the air. We're not even talking about the tsunami yet. Okay, just the air shock wave went around the Earth several times, and it's visible in many of the satellite images. Okay, yeah, so it just loops, but you can appreciate the scale of that. And just think from Malaysia, where would you drive to if this happened in Toba, for example? And Toba is a supervolcano, just so you know, right? So, normally you would think about volcanic eruptions as saying, okay, so a volcano erupted, yes, it put out a lot of CO2 as volcanoes do, right? But that's natural CO2, and it's been happening throughout history. And there's nothing we could do about it anyway, but it's natural CO2. But the important thing about most volcanoes is that they put out a lot of sulfur. And these sulfur aerosols actually go up and go around the planet, and I'll show you some maps where we actually can track that. And they cool the planet, right? But why is this one warming the planet? The reason is because it's a weird eruption, right? The cloud attained an altitude of 57 kilometers. They were actually able to do parallax from satellite images to get this height. Because the normal methods for measuring in the stratosphere, we've got things like sounding balloons and all that up in. Where is the stratosphere? Stratosphere, our atmosphere ends at about 18 kilometers. Then at the equator, at the poles, it's lower. 18 to 20 kilometers, we hit the end of what the atmosphere where climate happens. After that is stratosphere. Stratosphere goes from 20 kilometers up to 50 kilometers. After that, we actually get into the mesosphere. I mean, that's 99% of the atmosphere is below 18,000 feet. The rest we're talking about less than 1% of the atmosphere. It's really, really sparse. This broke through that. Previous record holder, Pinatubo, 40,000 feet. So this is 57,000 feet. Okay? So once again, why didn't we hear about it? Okay? So height alone, not so much of an issue. Size, compared to Australia, you should have heard about it. I mean, this is big. If it had happened anywhere in Australia, it would have, caused a big stir. Okay? 10 cubic meters of material. Boom, like that. Just thrown up in the air. 10 cubic meters of material. I was not 10 kilometers by 10 kilometers, but 10 cubic kilometers is more like 2 kilometers by 2 kilometers by 2.5 kilometers. Still, that's a lot of stuff to be thrown up in that short of time, right? So once again, that stuff should actually be cooling us, and it is. But there's a problem. As I said, it's a weird eruption. Why? You have to appreciate this. This blue line is the original profile before the eruption, and the red line is the profile after the eruption. Note the difference in the scales. This is 800 meters from top to bottom, but the width of the crater is 5 kilometers. You look at the bottom scale. Right? From here to there, it's 5 kilometers. So you had 5 kilometers, about 35 meters below the surface and maybe 150 meters below the surface. Okay? That blew up. If it had been a regular volcano trying to erupt at 1 kilometer deep, the water would have kept the eruption, the pressure would have kept it, would have roiled up, it would have released steam and gas, etc., but you wouldn't have had this. Had it been a terrestrial volcano, it would have been very different too. But what it was is, the moment this cap blew, all the seawater rushed in, and the steam flashed to steam, and resulted in the steam explosion, which moved 146 million tons of water up into the stratosphere. And water is a huge greenhouse gas. Okay? It doesn't stay there that long, but the amount added 10% to the existing stratospheric water. We should add another 10% to the water up there. So that's going to be circulating the globe and keeping the heat in. Immediately. Right? So tonight, heat is going to be trying to escape. And it's going to go through the atmosphere, and it's going to hit the stratosphere, and it's going to go, oh, sorry, I can't get out. I've been absorbed by a water molecule. And it's going to take years to get back. Because this water is in the form of vapor and it's up there. But it's very rarefied anyway. All right? So, strange set of circumstances. Yeah, it's coincidence that this happened. But it happened. And like I said, if it was a normal volcano, we only worry about sulfides. Oh, good, we'll cool the planet down and ash. But, and the tsunami, by the way, was interesting also. Because when you're just 35 meters below the surface, you can generate a huge tsunami, which it did. We don't know how many people were killed in the Tonga archipelago because no one was there to record and nobody found anything, survivors, etc. 2 people were killed in Peru. And that's, how many thousand kilometers away. So, huge wave. All right, once again, why didn't we hear about this? So once again, so what happens in this world is so well curated. It's processed, it's refined, what do people really want to know, and then it's put out there, and then we consume it, and we think, okay, it was a volcanic eruption, 5 people, not too bad, more people have been killed when smaller volcanoes erupt. But this thing is a monster. Had it happened anywhere else, we'd be in deep doo-doo. Okay, so this is together with the El Nino. This is another thing. Okay, we've also had things that we've been doing our own measures to cut pollution, protect air quality. So we've been going from Euro 4 to Euro 5. We're cutting out the sulfur. Good. No acid rain, less acid rain, etc., etc. But we're putting less sulfur aerosols in the atmosphere and more light is getting through. That's something that we're doing. Then there are natural things. We normally have dust storms that bring Sahara dust into the atmosphere and help cool many parts of the world that actually receive a fair amount of sunlight during the summertime. Right? But we had weaker than normal air currents and we had less Sahara dust. And that's, in my book, the 4th and final reason why 2023 was as hot as it was. And of course, moving into 2024, because many of these things are not going to be solved immediately. Right? Particularly the volcanic eruption, which, like I said, has been curated so well that it's off our radar. Also, so once again, the scientists, when we look at these things, we wonder why people don't understand why things happen, and the reason sometimes really is that our own institutional frameworks that record the news, that process the news, that deliver the news to you, don't join the dots for you. They just say it's a headline. 2023, hottest 24 months ever. Okay? But you need to go back behind and look, okay, what happened that year? And then sort it all out, right? So, as directors, when you see these headlines in the news, okay, hopefully this can help you think about, what is behind this headline that's actually being curated out. Oh, this is not necessary. They want to know about that. They don't need to know about that. Not important, right? But volcanic eruptions, as see later on, are happening everywhere. And sometimes they help us with climate change, sometimes they hurt us with climate change. And you may think it comes out in a mix, but once again, if you think where your supply chains are, you think of who your customers are, and if impacts of climate impair their ability to continue using your products, buying your products, purchasing your products, whether you sell them raw materials, etc., their industries, then these things will start begin to make sense for you. All right. The take-home message is what happens in the Pacific does not stay in the Pacific. Okay? This is the dust cloud. Dust cloud's cooling, but it won't stay there long. The dust cloud will settle out. What will stay there is the water. Because it's high. We've never seen water blown that high before, right? And nor that much. And once again, it was a fluke of the type of eruption that we had. Right? I'll show you 3 more eruptions. None of them do this. Okay? All right. Now, I want to change gears a little bit because I want to talk about move from the Pacific system to the Arctic system, the other quote-unquote big system. This slide normally appears very, very much earlier in my talks. In fact, it appears almost at the beginning of my talks, because it basically tries to explain that it's not climate change that's killing us. It's the rate of change that's killing us. All right? It's like when you fall off a building, it's not the fall that kills you, it's the rate of change at the bottom. When you go from terminal velocity back to zero, that's the part. I ask you to look at this graph, it looks fairly symmetrical. It's a bowl from left to right, right? Only problem is the scale is changing. These are 100 years apart. So this span in the fifth panel is only 400 years. Okay? Then it goes to tens of thousands of years, hundreds of thousands of years, millions of years, and then tens of millions of years. Okay? So, if you look at the ice ages, hard to see on the scale of tens of thousands of years. Basically, we're coming out of an ice age, right? But if you look on the scale of hundreds of thousands of years, then the ice age cycles become very regular. You can see them nicely. Every 100,000 years or so, we'll have interglacial, and then we'll have glacial, interglacial, glacial, high, low, between 180 parts per million and 300 parts per million of CO2. Right? When we hit the millions of years, this thing gets compressed. But what you see is that when we have two ice caps, both the north and the south, look at the top of the screen, you see that that's a continuous line. That's an assumption, by the way. That's an assumption. These two gray lines at the top, we are assuming that we've always had a north pole with ice and a south pole with ice, even in summer. Okay? If it goes away in the summer, then ta'achi anymore. Right? That's why it gets dotted and then it fades off. But with two ice caps, this is our temperature range. Right? And as you can see, we only came along 300,000 years ago as a species. So were we responsible for any of this? No, we weren't around yet. Maybe our ancestors were. But for a long time, we had no effect on our temperature until about here. So you notice that this is partly in the present and recent past and partly in the future. Why? Because we need to think about where it is that we're going. Right? If I continue further, when we see that lower line, northern hemisphere ice sheets fading away, then we are left with only the southern hemisphere ice. Because global temperatures are average global temperatures, increase of 3 degrees doesn't mean that this temperature here is going to increase 3 degrees. Okay? It means that there are other places that are no longer as cold as they were. So with no Arctic ice, this is the range, about 5 degrees warmer. Finally, with neither North Pole ice nor South Pole ice in the summertime, about 10, 12, 15 degrees warmer. Okay? Average global temperatures. Right. Now, what all this does to the rest of the land masses, etc., by the way, at 50 million years ago, India had not collided with the Eurasian plate yet, so India subcontinent was still floating around in the Indian Ocean. Right, so other things are changing as well. Right? But the idea is that when we think about having no Arctic ice in the summer, that's important, because that's kind of where we're headed, right? But, as I said, it's an issue of how long it takes, okay? Last time we had no Arctic ice between 1 and 3 million years ago, all right? Systems have had millions of years to adapt to that, to change with that. And just so you know, if I wanted to show, using this scale, 400 years, 4, 8, 12, 16, 20, if one screen was 2,000 years, to show 50 million years, I would need 25,000 screens. That's how asymmetrical this graph actually is. And if you look at any interval, it will almost be a straight line. There are a few exceptions. When an asteroid comes in, of course, it's going to change. Okay, but the most part you will see it's all straight lines. Very few of them are going to look like this over the span of 400 years. Because things change over the scale of tens of thousands, hundreds of thousands, millions of years. It's not the fall, it's hitting the ground. Okay? So, and once again, the idea here is to think about the Arctic because it is a large system and it's thought of as a sea system. That's the Arctic Ocean, after all. And we're talking about sea ice. So some dismiss the idea that sea level rise. It's sea ice. Sea ice melts, the icebergs disappear, but they take the same amount of water in terms of space. Yes, there is some expansion, thermal expansion, but it's not the sea ice going to kill us. They forget about Greenland. Greenland is not sea ice. Okay? And we've made the assumption that Greenland has, as far as we know, been mostly ice covered. Right? Yeah, there's some stories about why is it called Greenland, and it was green at some point in time, etc. But as far as we know, really, the assumption is it's been ice covered. The yellow extent is the extent in the 1850s, at the beginning of the Industrial Revolution. Okay, so we can see that you know that's the summer extent. The winter extent is bigger. Right? So it grows in the winter, it comes back in the summer. But the critical one is the summer one. So the summer extent of ice in 1850s is there. Now, of course, it's thinned quite a bit. That is the North Pole. I put it there to give you a bit of reference, right? And we are losing it at the rate of 13% per decade. Sounds slow, but it's the kind of slow that's inexorable. And a decade goes by very fast if you have kids. Okay? And just the past 3 decades alone, okay, the oldest and the thickest ice has decreased by 95%. So it's not something that's necessarily linear because, as Sharath mentioned, there are positive feedbacks, right? The more water you expose, the less light, sunlight you reflect back to space. This image is white there because that light that hit the ice is gone back out to space to hit a camera in a satellite. That's how you know it got out. And if it got out, it was never converted into heat and never blocked by greenhouse gases. Okay? So I love looking at very bright Landsat pics because it means that light is getting out. And light gets out before it becomes heat, wonderful. That's why all our roofs should be white. But this is an issue. And 2040, where do we see that number last? Okay? If we're ice-free by 2040, right, then we're going to be tempted to use that as a shipping route. And once again, there are issues with shipwrecks and things, especially when they're icebergs. So, you know, Titanic theme playing, etc. So all of these things, once again, of course, technology is improved, right? No longer have someone in the crow's nest looking for icebergs, but nevertheless, lose power. We just had a ship, right? We had a ship lose power and block the Suez Canal. We had a ship lose power, and what happened again recently, right? Lose power and hit a bridge. That's right. Okay. So all of these things that, you know, it's like unintended consequences. Yeah, we didn't have it, but technology is so good nowadays, so reliable, etc. But things happen. So things happen that are our fault, and things happen that are not our fault, but things happen. And as directors, we're kind of paid to think about those things that, while not predictable, are foreseeable. Yeah? Okay. So what else? If we're talking about the Arctic, we need to think about what happens when water freezes in the Arctic, right? So we have this so-called ocean conveyor belt. Basically, the sea surface is got the warmest temperatures. The sun hits it, our rainwater flows into it, it's all warm. We've picked up heat from the land, we've picked up heat everywhere, and we've got these warm currents, and these warm currents circulate up into the polar regions, and at the polar regions, they are supposed to hit cold air, supposed to freeze, right? And an interesting thing happens when you freeze seawater. Only the water freezes. The salt doesn't. So right below the frozen water is a layer of extra salty water. And that extra salty water is heavier. And that's what causes it to sink and drive back down the cold currents that bring that water back to the equator where it can be recycled again. Okay? So we already have, just in March of last year, studies showing that because less seawater is freezing in the Arctic, less salt is being liberated to make the water heavier, to help it to sink, and then drive it. So we're weakening a number of very, very important currents, the Gulf Stream, a number of others. Now, we mess with those, we immediately mess with fisheries because these upwelling cold water are what bring up nutrients to feed a lot of these natural ecosystems, the sardine industry, mackerel industry, all of these things. And then they feed higher and higher food chains from the krill on up to whales. Okay? So this is a problem. And it's associated deeply with the poles. Now, this was a surprise. Okay? Because, like I said, science is strange. Scientists go out there, they might collect data, they might not have the technology to process it, they might not have the time to process it, but they at least have the sense to put it in a freezer. Okay? So in 1966, an expedition to Greenland drilled through 1,300, so it's about 1,600 meters is a mile, right? So about 300 meters short of a mile. There was that much ice, right? And then below that, they pulled up a 12-foot, 4-meter core of ice, soil and rock, right? And that's it. And forgot about it. I mean, how many scientists who are alive now were alive in 1966 and on that expedition to Greenland, right? But they found it in Denmark in 2017, and they put it in a pipeline. It was finally analyzed 2023, right? And what they found was twigs, mosses, leaves, and seeds, which means there were long enough summers in that part of Greenland, which we've always been assumed to be ice-covered, okay? All right? 416,000 years ago. We weren't around. Remember, we only came about as a species 300,000 years ago, and for a long time we were just hunting and gathering. Very little impact, okay? But naturally, Greenland was green just before we came along, okay? And on that scale, this is not long. It's a blink of an eye compared with how long. We've assumed that the Arctic has been frozen for over 1 million years, right? Now, this is the interesting part. Where this soil was pulled to be free of ice, that ice would have already resulted in sea levels at 1.4 meters higher than they are now. Which means all the coastal cities now, forget trying to save Jakarta. And whatever plans you have for a new capital, figure this in, all right? But this is the best case scenario. Because this core happened to be pulled out where that base was. The scientists then did not have the foresight to say, I'm going to run a whole bunch of cores from the lowest part of Greenland to the highest part of Greenland and see, so we are assuming that the other parts of Greenland were still ice covered. If we assume this 1.4 number. If Greenland was completely ice-free, it would be 7 meters higher, all right? But this is the part that's scary. The current CO2 levels are already 1.5 times higher than the CO2 levels were 400,000 years ago. So at those CO2 levels, it was already warm enough to melt Greenland to have 1.4 meters at least higher sea level. Okay, so we are going to 1.5, going to 2. Okay, so we have to really reconsider the time frame for doing things that we have, right? So as directors, where are your assets? Okay, how vulnerable are they? Do you, can you look at your land bank and re-examine that? All right, because if we lose all of Greenland, and it might have been all of Greenland, 400,000 years, we don't know, because nobody pulled the course. Yes, sir.
Not only the land bank, it's a connectivity to the land bank.
Oh, yeah, absolutely. And so it's land bank plus all the infra, right? It's everything. It's water supply, it's energy supply, it's where, your next development needs everything. It needs people, it needs energy, so it's the works, right? So when Sunita said, do the science, I'm like, do you know how hard that is? 99% of the papers that come out have, second order partial differential equations and cloud. No, but I was able to find these studies that actually, that hopefully, you can bite on and understand that science is not perfect. Things reappear after years of being stored away, but they change our understanding gradually and improve our understanding of these systems. So now we can discount the fact that, that gray line at the top that said we've always had ice in the Arctic Circle, right? We need to rethink that and reprocess that. Yes, ma'am?
Yeah, a lot have been done, studies have been done on Arctic. What about Antarctic? Anything has been done?
Yes, and lots of work is being done. And yes, the Antarctic has been ice-free because we know that. And we do have the evidence of that. We have fossilized tree trunks, tree ferns, etc. So we know. But that is so far back in the past that, it was Gondwana. It was before the continents broke up. Gondwana, Pangaea. So we are not there yet. And we don't think we'll be there for a while. But the part that is concerning is if we have accelerated warming that gets down, if years like 2023 have an inordinate impact, if we have underestimated the linkage between having a hot year and losing ice in the Antarctic, right? And that's what I'll talk about, climate sensitivity, all right, in a bit. That is going to sort of argue, the scientists will start arguing about that, right? And the strength of that linkage. And that's what's going to become important. Because Greenland is only one land ice mass. The biggest one is Antarctica. And yeah, the world was completely different place. Didn't stop life from happening, dinosaurs, but we weren't around. We're not part of that. And the most important thing is that we really have curated the planet for our survival. So there are more food animals, agriculture animals alive now than there are natural wildlife, right? So, and we rely on that. Okay, so once again, when we talk about climate change, we're not talking about extinction of human beings. We are talking about human misery and suffering, right? I also have slides dealing with migration. I have slides dealing with deaths due to floods and landslides, all of which extreme weather event related. The numbers are astounding. So once again, these things are curated. They come up as headlines. 56 people killed. Like yesterday's papers. Floods in Pakistan, number of people killed. I met a gentleman from Pakistan this morning, already talking about it, right? But how much of that, after being curated, actually enters our consciousness and then enters our decision-making processes? Okay, that is, I think, one of the things that we need to deal with. Okay, so what does not happen in the Arctic? In this case, freezing. Okay, we want freezing to happen in the Arctic. Okay, it does not happen, it does not stay in the Arctic. It comes out and impacts the rest of us, like I said, through the thermohaline currents, through these other impacts, such as warming of sea level rise, etc. So sea level doesn't rise in the Arctic, it rises everywhere. Okay, not much time left. I'm supposed to go until 12, so we've got 15 minutes, thereabouts. Okay, any questions before I change gears a little bit? Yes, sir.
Harry, I mean, you go back to the slide where you show the whole, variability of temperature. There is that period where there is stability, that yellow line.
Yes.
That's like homeostasis, right? Because it stays in a narrow band. I don't think what you have here is that agricultural revolution took place before industrial revolution, because things could grow.
Mm-hmm.
So here's my question. If you go then to the right, where it starts to go, temperatures going up 3, 4, whatever, 5 degrees, at which point do we lose food crops, vegetation, forests, whatever?
I do not know the answer to that question. What I can say is that because no scientist can specialize in all of these epochs, right? You can see that the curves are credited to different scientific papers by different scientists who studied the world as it was in different time frames. Basically, everything in the past, you've got to go down and find, you've got to move to archaeology, basically, and find those answers. In fact, if you look at archaeological studies of civilizations that have tapered out, the Mesoamerican civilizations, you will actually see the rise and fall of agriculture. Okay? And it can be because of salination, it can be because of irrigation. So the science was not as sophisticated as it is now, the technology was not as sophisticated, but what science and sophistication and technology allows us to do is basically defray. We are slowing the onset. Every irrigation event is going to leave salt on your land. It's just a matter of how much. It's just that if you use better and better water and better practices of flushing it, or you allow, best of all, allow floods to come. Dirty word, right? Now we want to channelize the river. Don't want floods to happen, right? No, floods have a purpose. They put sediment on the land, they put nutrients on the land, and they remove salt. Okay, so once again, I think that if you want the answer to that question, you can probably find it in some of the archaeological work that determine why some of these civilizations, Mesopotamian, Mesoamerican, some of these others, why the agriculture failed. And it was the failure of agriculture that in many cases drove them. That led to food conflict, which then led to geopolitical conflict, etc., etc., etc. And it's happening now, which is what drives the migration from the African continent across the Mediterranean into Europe. Okay, so sometimes hard to get concrete links, but the links are there. Okay, yes.
Yeah, so we are also seeing like with the El Nino and El Nino,
La Nina,
La Nina effects over the years, how certain parts of the world when they don't have enough rainfall or they have too much rainfall is affecting crop production and hence food, and then if you look at, like us, some of our companies who are producing agri-chemicals, it affects our sales.
Yes, absolutely. So once again, not just your supply chain, but your customers, right? So 3 years of La Nina in a row, 2020, 2021, 2022, good for us in terms of our rainfall, etc. But if you rely on chicken meat as part of your feedstock, then you need chicken feed. And over the 3 years, 2020, 21, 22, the sources of corn meal and soybean meal in Argentina and Brazil, where we get most of our chicken feed, began to dry up because that's 3 consecutive years of drought for Argentina. Right? So, but you only hear it in Malaysia as, harga ayam naik. Right? And then the minister will say, it's because the harga makanan ayam naik. And then, but nobody traces it back to the fact that it's because we're having 3 consecutive years of La Nina and 3 consecutive years of drought in Argentina and Brazil, where they grow the corn and the soybeans as the source of this stuff. Okay, so hopefully, I always wonder when I give a talk whether I'll see these faces again, because quite frankly, these things are big, and they disappear because our news is curated so well, and our information is curated so well, and there are all these bottlenecks that things have to pass through, and somebody somewhere is deciding for you. You don't need to know this, okay? Yeah.
I
So.
was thinking what you're talking about. I think it seems that the problem has escalating so big, and on the part of bring it back to reality, on the part of board members, what you are here for. What is the expectation? What can we do to mitigate, or at least to educate?
So I think the first thing and your being here is already part of it, and the fact that you are appreciating some of these big picture things that once again are not part of your normal news feed. So the idea is that when you see a headline, okay, do you have a go-to person behind that you can say, hey, why did this happen? Because it's been a long time since I've listened to public radio. I was in the US for 17 years, okay? But at least on public radio, they had segments where they did analysis of the news, all right? Who does analysis of news now? Who does, and do we have time? We only want a TikTok video. If you can't tell it to me in a TikTok video, it's not important. Yeah, but once again, the idea is that sometimes even by the time the feeds get to KS, they're already curated. Somebody's already decided that's important, this is not important, that's important, this is not important. But I'm just hoping that as directors, that you begin to see some of these things and help them to move along. I don't have very much time left, so let me very quickly move into the next, like I said, big argument. And this argument really has to do with what are called super cooled liquid clouds. Super cooled water clouds, SWCs. All right, and once again, this is also new research, but bottom line, long story short, they don't reflect light back to space like regular clouds do. All right. Yes, they do have a problem for aviation safety because they do ice up wings, but modern aircraft have heating systems in the wings to melt it as it goes, right? But the big thing is this Earth's radiation budget, right? We do need to understand, particularly now when we're having solar maximum. I didn't put that in because at least it's out there now. Solar maximum, yes, everyone's talking about the northern lights, the southern lights. Okay, it's out. Somebody's decided, people know about this. Okay, so we are at a solar maximum, but how much of that is reflected back to space? That is a function of our cloudiness. But if we're just looking at clouds and not understanding that there are different kinds of clouds, so the issue now is for this super cool water, which is 8% of all the clouds up there, 8%. Of the clouds, how reflective actually is it? And that's the current argument. And the other question is this 8% increasing, decreasing? Is it something that's going to change with changing climate? Because we need to worry about that as well. All right? Is the fact that when we have warmer conditions, there's a greater possibility of having these super cool water clouds, or is it the other way around? All right? So this is hot now. Currently, it's done empirically. It's a formula, and so it can be biased, right? So this quantification detection is all over the journals now. And like I said, it's talking about second-order partial differential equations. I'm not even going to try to understand it myself, all right? But it's important to note. So what's E there? F is ocean. E is these clouds. And then A, B, C, D are different types of clouds that do reflect. So there's a lot of work going on this using remote sensing right now. Okay? This is the only formula I will show you. Basically, climate sensitivity is the initial warming plus, as I showed, the feedbacks. Okay? Feedbacks can be positive, can be negative, but when we talk about climate sensitivity, we're just saying this. Double the current greenhouse gas concentration in the atmosphere, let it equilibrate, what's the temperature? Right? Simple question. But when you get all the scientists in the room together, they argue about it for the rest of their lives, their natural lives. And it's a good thing. Because then the most important thing is what comes out of the argument, actually they need to tell us. Then we can correct the projections of what the temperature is going to be like. Okay? So the amount of planet will warm and accounting for various feedbacks. And you've got all these processes, right? So there are a number of different things that go into this climate sensitivity. And this sensitivity, like I said, once again, it's going to tell you where you are in terms of this band, or even whether you're already outside the band, all right? But the gray bar in the middle is the IPCC range. If we double greenhouse gas concentrations from the pre-industrial time, 1850s, then this is what we expect, anywhere from actually 1.5 to 4.5 degrees. But it looks like everything is kind of centering on 3, and we're not quite double yet. So we're going from about 180 parts per million, 180 times, actually no, we've passed 400 parts per million. Yeah, we've passed 400. So some of the effects, some of the data are pulling us in this direction, some are pulling us in this direction, but you can see going from the dot to the fat bar to the thin bar, where some of the outliers might be. And the things we don't know, things we can't predict, like the volcanic eruptions, okay? I will put Hanga Ha'apai way out there. We didn't expect that. We didn't predict it, nothing. And it could have been any other kind of eruption, which would have had the opposite effect, cooling effect, rather than a warming effect, okay? So there's nothing sacred about the science is like that. And I think all of us know it. But we really need to start bringing it into the corporate board culture and start talking about it while at the same time admitting that even scientists don't know a lot. There's a lot that scientists don't know, but they're constantly finding out. And we need to bring the board up to that level and make them aware that these are some of the probabilities, these are some of the possibilities, and these are some of the things out there that, while not predictable, are somewhat foreseeable. Okay? So, if Hanga Ha'apai does erupt again, at least we know there's 800 meters of water on top of that will help keep that eruption down and help keep that water from being blown up into the stratosphere again. Okay? And then there's dumb luck. We've got 3 volcanoes. Okay? Ruang. And this is an image of sulfide concentration in a very nice website called windy.com. Okay? All these sulfides came from the Ruang volcano, and I watched day by day as it spread. This is after 2 days. By 4 days, it had reached Sri Lanka, India. And then by a week, so as the world turns, right, the prevailing winds just carry it, and then they disperse it north and south. Sulfide aerosols, as you know, reflect sunlight. Okay, I'm already grateful for the lives that would have been lost to heat waves because this happened. And it's not just this volcano. In our neck of the woods, there are 2 other volcanoes that are not erupting like the Hanga Tonga one, but either they are mature cones in the sea or they're mature cones on land. Ibu is in the middle of land. Ruang is a sea volcano, but it's above the sea, so it's not going to be a problem, right? So dumb luck, but brings the temperature down, right? Definitely life saved already, because you look at the death toll from the heat wave recently, 2024, Thailand alone, I'm not counting Pakistan, places like that, okay? Pretty bad, right? So not under control, but we couldn't have done better had we even planned it, okay? Right? So sometimes the dice roll your way, sometimes you don't, Bet with the house. Okay. If you bet, if you're allowed to bet. Okay. So that kind of brings me to the end. It's 11:59. I don't want to keep you over time, but basically, we haven't had the bottom fall out of science on any of these issues yet. Okay, we haven't had a major theory or a major hypothesis debunked. Scientists continue to pore over it. They continue to question. That's so important. Okay, there can be no muffling of voices that disagree with the prevailing wisdom. You must always ask questions, particularly the ones that people don't think should be asked. Ask them, answer them, be proven wrong, be willing to move on. That's what the scientific process is about. The projections have proven to be robust, both with the long-term processes, historic processes, as well as the short-term events. Okay, so once again, immediately when Hangga Tonga erupted, there were already people working on why on earth it was so different, right? And in answering those questions, adding to the body of information that can help us to understand. Now, what's the percentage of volcanoes that erupt that way? We can already go and check how many volcanoes are shallow, just below the sea surface. We can already, so those numbers can come in, and then those probabilities can come in. We overlay that with seismic activity, right? We get even better confidence. So all of these things, the scientific community has the responsibility to be communicating to the rest of the world, and as board members, I think you should be one of those groups that's picking it up. The cycles, okay? Whether it's and by the way, the El Nino, La Nina, the ENSO, the El Nino Southern Oscillation, it's only one cycle. There's the Indian Ocean Dipole Oscillation. There's even an oscillation that moves around the world, around the equator with time, all right? And so that the scientists have a responsibility to make these things digestible, to make them understandable, to put them out there, overlay them on the current expectations, anticipation, and then make you aware of all the wild cards that could be thrown in, okay? Well, the last one is basically, things are out of your control. But the more volcanoes, see, people ask me, every time a volcano erupts, I'm very happy. Every time we have an earthquake, I'm very happy. I'm very happy. Because every earthquake reduces the intensity of the next one. Okay, if you didn't have an earthquake, the stress would just continue building, right? So earthquakes, volcanic eruptions, good. Okay, floods, natural. They have a purpose. Let them flow where they want to flow, or at least manage well. John McPhee, a while back, I read his work, Control of Nature. Fighting the way things are has seldom ever worked. Okay, and people sometimes think that nuclear power is fighting the way things are, but no. Okay, these are natural processes. You may think that geothermal is very clean energy, but it comes from, the decay of radioactive material in the Earth's core. Solar energy is beautiful, but it comes from fusion in the sun. So all of these things, you'll see these battles being fought about what humans should be doing, what humans shouldn't be doing. I think we should save a lot of energy and focus on trying to work with rather than work against. We see the same thing with supply chains and all that. You're not supplying me low carbon materials, I'm going to cut you off. Versus, how can I help you as my supply chain to clean up your act? Here, use the SEDG, the Simplified ESG Reporting Guidelines. You use this, use that, work together and solve the problem. That, I believe, is all I have. I thank you very, very much for your time and your attention. Hope it's been useful. Thank you.
Well, I've got no more questions to ask. I think I was going to say, what would you give as a wrapping up? I think Dr. Gary has actually wrapped it up for you. So if you see the QR code here, please give some input and quotes on this session. It's invaluable for us also to get some feedback and how you see. in relationship to the boardroom and in terms of decision making and direction, I think what is illuminating here is the fact that we actually have to build in resilience into the board, in the sense that preparation and allowing for the risk factor of climate change. In terms of cities that are also moving in this direction, New York is building what is called the Big U. That's because they want to protect from the 1.5 meter rise. Penang South Island is also built on 1.5 meter rise. So it's actually a preparation for that, and the greening of on the perimeter of that has considered the biodiversity, etc. Lack of biodiversity that will be lost also. So these are some of the things that will start to creep into your decision making. So a round of applause, and also please join us as corporate friends at Climate Governance Malaysia. It doesn't take too much, and we do a lot of work. We have the rest of the masterclasses coming up, but we also have, I think it's in September, we also will be having a conference in Bangkok. And if you didn't catch it last year, we have basically this follow-up which is covering quite a lot of things. So we appreciate if you become a friend and support us, volunteers who are on this. And before we go, we would like to take a picture on the bridge with all the masterclass people that's attended here, so before you leave. And finally, a big thank you to FIDE Forum for basically bringing us this climate governance